Speaker this morning is William D. Phillips. He's a fellow of the Joint Quantum Institute, which is a cooperative endeavor of the National Institute of Standards and Technology, or what we call NIST, and the University of Maryland. At NIST, he heads the Laser Cooling and Trapping Group in the Quantum Measurement Division. And at the University of Maryland, he's a distinguished professor of physics. And at the Joint Quantum Institute, he's the co-director of an NSF-funded Physics Frontier Center studying quantum phenomena across a subfield of physics, subfields of physics. Lastly, you should know that in 1997, Dr. Phillips shared the Nobel Prize in physics for the development of methods to trap atoms with laser light. And this is going to be a very fun talk, as you can see from the demonstrations here. So I'll introduce Bill Phillips, please.
Merci. Bien que je vais faire la conférence en anglais, je vais commencer avec quelques remarques en français. Bon. Je suis très contente d'être ici à UNESCO pour cette célébration de l'année internationale de la lumière et je suis surtout contente d'être à Paris pour cette cérémonie parce que Paris est la ville lumière. Et à Paris, la lumière est partout. Et la lumière est dans tout. Et c'est seulement avec la lumière que nous pouvons vaincre les ténèbres. Seulement avec la lumière que nous portons en nous, chacun d'entre nous. So, enough philosophy, now let's go to science. Einstein Einstein, time, and light. So first of all, I want to mention the people that I work with on a daily basis, Gretchen Campbell, Paulette, Trey Porto, Ian Spielman, and the people who have supported this work over a long period of time, the Office of Naval Research, NIST, and most recently and very importantly, the National Science Foundation. And I would like to echo the message that we heard from the director of the National Science Foundation yesterday about the importance of basic research if you want to achieve practical results. Well, Einstein, time, and light. This is the International Year of Light, and this beautiful painting by Giovanna Rosario, who is the wife of Massimo Inguscio, who many of you know, celebrates light in art, in the same way that we celebrate light in science. And as we heard yesterday, there is often not such a fine line between art and science, and we celebrate both aspects of things. And one of the things we're celebrating today is this series of anniversaries. I've borrowed this slide from John Dudley, showing the anniversaries that we're celebrating from 1,000 years of optics with Ibn al-Haytham, and coming up closer to the present day with the cosmic microwave background discovery and the development of optical fiber technology just 50 years ago. And as I go through, I think you'll see that each one of these anniversaries is recalled in the work that I'm going to be talking about. Well, Einstein, time and light. What does Einstein have to do with time? Well, Time put Einstein on the cover of their magazine as the person of the century. And I think we would all agree that it was a good choice. And so many of the things that Einstein is remembered for have to do with light. He came up with the idea of stimulated emission, which is the basis of the laser. General relativity is one of the anniversaries that we celebrate in the International Year of Light. Bose-Einstein condensation makes atoms behave in many ways like lasers in their wave-like property. And of course, the thing that Einstein got the Nobel Prize for was light as particles, the photoelectric effect. But probably the thing Einstein is most known for is his theory of special relativity, which is a 110-year anniversary this year, and it was all about light. And with it, Einstein changed our very conception of space and time. And he did this by asking himself a question that I suppose people have asked themselves since the beginning of time. What is time? What is this strange thing that constantly seems to be flowing, yet is always in the present and will soon become the past? And what Einstein said was that time is what a clock measures. Now, this may seem like a silly answer, but by taking that idea seriously, Einstein was able to come to remarkable conclusions about the nature of time. Let's think about a clock in the way that Einstein thought about it. Now, remember what Steve Chu said yesterday, that Einstein took seriously the idea of Maxwell, that the speed of light was the same regardless of the frequency, and extended that to say that the speed of light was the same regardless of the observer. So imagine that you've got a clock that ticks every time light bounces between two mirrors. Now, if you take seriously the idea that light travels at the same velocity for all observers, then if I am moving with this clock that has light bouncing between the two mirrors, I see it ticking away just as I would if I were at rest compared to you, because moving at a uniform velocity changes nothing for me. But what does it look like for you? For you, it looks like the light is following this zigzag path, and because light always moves at the same velocity, it must take longer for my clock to tick as seen from your point of view. That means that time is running slower because, after all, time is what a clock measures. And using this idea, Einstein was able to come up with his idea of time dilation. Now, if time is what a clock measures, let's go back to the PowerPoint, please. Let's stay with the PowerPoint until I tell you not to. Okay, so if time is what a clock measures, then time itself slows down with motion, as do all clocks. This is what we call time dilation. Now, you may ask yourself, well, what kind of clocks do we have? Well, we have a tremendous variety of clocks, and we've had different kinds of clocks throughout history. The earliest clock is the rotation of the Earth. Now, the rotation of the Earth made it appear to ancient people that the sun was rising and setting, and this allowed people to tick off days. I think it's a wonderful point that the earliest clock is the sun, the rising and setting of the sun. So the earliest indication that we have of timekeeping has to do with light. And as you will see, the best clocks today are clocks that depend fundamentally on light. So it's a wonderful thing for us to be talking about in the International Year of Light. But in the meantime, we had these various kinds of mechanical clocks, and all of these clocks are imperfect in one way or another. But the best tickers and the things that make the best clocks are atoms, because there are energy levels in every atom, and that corresponds to a frequency. That is, the difference between energy levels corresponds to a frequency. And that frequency is the ticking frequency for an atomic clock. And while every quartz watch is different, every cesium-133 atom is absolutely identical to every other one, and they're very little affected by the things that might change the timekeeping of mechanical clocks. And so for this and other reasons, atoms make the best tickers. Well, how good are these clocks? For less than 100 euros, you can buy a quartz watch that is better than a part in 10 to the 6. That would be 30 seconds in a year. But for about 100,000 euros, you can buy an atomic clock that is good to a part in 10 to the 12, a part in a million, or 30 seconds in a million years. Now, you may wonder, who wants to pay $100,000 for 100,000 euros for a clock? But think about this. You pay 1,000 times more money, and you get 1,000,000 times better performance. I think this is a tremendous bargain. But you still may ask, why does anyone need a clock that good? Because after all, most of us don't need a clock in order that good to know when it's time to go to lunch. But in fact, I want to convince you that you're very happy that somebody is keeping track of time that well. Here's an advertisement from a magazine that says, if you buy our car and you get into trouble, relax because help is only 10,000 miles away. And the 10,000 miles is the orbiting altitude of the satellites of the satellite navigation system, or the GPS system. And how does this work? Well, we have a constellation of satellites, 24 satellites, 2 of which are shown in cartoon here. And there are clocks, atomic clocks on board. And all those clocks are synchronized. Now let's just imagine for a moment that you have such a clock and it is also synchronized. So all these clocks keep the same time and they broadcast information about what time it is and about where they are. So when you receive a signal from one of these clocks, you know how far away you are from the clock because you know that you have the same time, but it took a certain amount of time traveling at the speed of light for the signal to get to you. So you read a different time on this clock, even though it's keeping the same time as your clock. That tells you how far away you are. That tells you that you are somewhere on this surface. Well, if you've got more than one satellite, as you always do, if your satellite navigation system is supposed to work, then you know how far you are from 2 different satellites, and you know where the satellites are, so you know where the intersection is, and you know where you are. Now, you don't have a clock, and we don't live in a 2-dimensional world, so in fact, you need 4 satellites to make up for this difficulty. But once you have 4 satellites in view, the GPS system allows you to tell where you are to within a few meters anywhere on the surface of the Earth. In fact, you can do even better than that, and if you take enough time, you can use it to measure continental drift. People use it for all sorts of things just to find their way around a crowded city like Paris. But you may ask yourself, what do these atomic clocks look like? If you were to go to one of our laboratories at NIST in Boulder, you might see an instrument like this. But what's inside? How does the clock work? Well, here is an oversimplified version of an atomic clock. We have a cesium atom. We shine microwaves, which are just light at a lower frequency, onto the cesium atom. And when the frequency is just right, it causes the cesium atom to change its state. And you measure whether it changes its state. Now, here's a slightly more sophisticated, although still simplified version. We have an atomic beam of cesium, and while the cesium atoms are passing in front of the microwaves, you irradiate them, and if they change the state, then you know that the frequency is correct. And that frequency is about 9 gigahertz. But the atoms are moving with a velocity of over 100 meters per second, and the laboratory in which this takes place, or the apparatus in which this takes place, is only about 1 meter long, so you only have milliseconds to make the measurement. So the limited observation time limits how well you can measure the ticking frequency of the atoms. Einstein's time dilation also limits you because the atoms are moving, and that changes their ticking frequency as far as you're concerned. So all of these things having to do with atomic motion limit the performance of these clocks to about a part in 10 to the 14. Now you may say, a part in 10 to the 14, that's incredible, but we want to do better. And in fact, we must do better if we're going to satisfy the needs of modern technology, science, and navigation. So, to do better, we have to make the atoms move more slowly. And in order to make the atoms move more slowly, we have to cool them down. Because the difference between hot and cold is the difference between fast and slow. The hotter something is, the faster the atoms and molecules move. And in fact, temperature is a measure of the kinetic energy of the atoms and molecules that make something up. Now, in order to illustrate this more clearly for you, we can now go to the demonstration. I've brought along, courtesy of my friends at Collège de France, I've brought along some really, really cold stuff. In here, I have liquid nitrogen. Nitrogen is the main constituent of the air, so that means this is basically liquid air. Unless you have worked in a cryogenic laboratory, this is the coldest stuff you've ever seen. It's so cold that compared to it, the floor on which I'm standing, this stone on the table, are red hot. What would happen if you poured cold water onto a red hot stove? It would boil, and that's what happens when I pour the liquid nitrogen onto this stone or when I pour the liquid nitrogen onto this floor. I was told that there might be ministers sitting in the front row, and I thought this would be particularly exciting for them. But if you have something this cold and you want to slow down the atoms and molecules, then it makes sense to use it as a refrigerator. So here I have a traditional container for hot gas. So what I'm going to do now is take this hot gas in this balloon and put it into the liquid nitrogen to cool it down, with the idea that, that if we cool down the hot gas, then it will make the atoms and molecules move more slowly, and if they move more slowly, then we can make better measurements of them. Now, I want to give you an impression of just how cold this is. Here is a Dewar flask. It's been sitting out all morning, so compared to the liquid nitrogen, it's incredibly hot. Imagine that you took a metal bucket and heated it in a fire until it was glowing hot, and then poured cold water into it. What would happen? It would cause the water to boil, and that's what's happening here. Don't try this at home. Okay, so while that is boiling away, cooling down the inside of the Dewar, let's cool down some more gas. Because after all, if we want to do experiments with slow atoms so we can make better measurements, we want to have lots of stuff. So let's... Okay. Okay, now let's go back to our Dewar. Well, you notice that a lot of it has boiled away, but I'm just going to top it up. Now, let's take this flour. This flour has been sitting out at room temperature. Imagine you took a metal rod and put it into a fire and heated it up until it was red hot. That's what this flour is. In fact, it's even red. And if you took that metal rod and plunged it into a bucket of cold water, what would happen? It would make the water boil. And that's what's happening here. So let's allow that to boil away, and while it's boiling away, let's put some more. What? Let's put some more hot air into our liquid nitrogen to cool it down, to make the atoms and molecules move more slowly. Because, of course, if the atoms and molecules are moving more slowly, then we can make better measurements on them. Okay, wonderful. Now let's see, what else can I do? Ah, yes, here's a nice rubber ball. Okay, a nice bouncy rubber ball. Let's see what happens when the rubber ball goes into the liquid nitrogen. Now, while that's happening, let's see. Let's get some more nitrogen in there. And I apologize for this noise because I didn't think there was going to be so sensitive to this microphone. So I'm going to try to make my tie move less. You know, I'm a geek, so I can stuff my tie in like that. Okay, now, here is a rubber band, a nice stretchy rubber band. I'm going to take this rubber band and dunk it into the liquid nitrogen. Now, you can't see, but what's happening is it's making the liquid nitrogen boil, as anything would. I pull it out, and it is frozen so hard, I can break it like it was a dry twig. But if I warm the rubber band up in my hand again, then you see it's a nice stretchy rubber band again. This stuff is really, really cold. And if you've got something that's that cold, then why not use it to slow down your atoms and molecules so that you can make better measurements. So let's do that. Okay. Now what else can we do? I'm sure that when you were very young and your mother was teaching you how to cook, that she emphasized to you that you should never, ever take a closed container of liquid and put it into the oven. Here we have a container. Here we have some liquid. And we're going to close it up. And compared to the liquid nitrogen, this room is an oven. Now, let's look at our flour. As you can see, the boiling has subsided. That means the flour has now been brought down to the temperature of the liquid nitrogen. It is frozen so hard that when I pull it out, I can crush it like it was made out of glass. This stuff is really, really cold. And if you've got something that cold, well, then why not use it to slow down your atoms and molecules so that you can measure them better. Okay. Now, how cold is this stuff? I've been saying that unless you've been in a low temperature laboratory, it's the coldest stuff you've ever seen. To understand how cold it is, we have to remember how physicists like to measure temperatures. We measure ordinary temperatures, the temperature of the environment, in the Celsius scale. Water freezes at 0 degrees. A cold day in Paris might be negative a few degrees. But physicists don't like dealing with these negative numbers, and so we have another temperature scale, the absolute or Kelvin scale, in which 0 is the coldest possible temperature you can have. Now, why is there a coldest possible temperature? Remember, temperature is about the motion of atoms. What is the slowest you can go? The slowest you can go is stopped. And therefore, there is a lowest possible temperature, and that is 0, absolute 0 on this scale. Now, it turns out that because of details having to do with quantum mechanics and Heisenberg's uncertainty principle, that even at absolute 0 of temperature, the motion doesn't really stop. But leaving that aside, just between friends, let's say that absolute 0 is when the motion stops. Measuring up from absolute 0, the temperature of this room is about 300 degrees. Ice melts at about 273. The coldest temperature ever measured on the face of the Earth for an air temperature was 185 degrees, someplace in Antarctica. The temperature of this stuff which is so cold that when I pour it onto the floor, it boils immediately. This stuff is 77 degrees above absolute 0. 77 degrees above absolute 0. Let's see what happened to our rubber ball. You remember how nice and bouncy the rubber ball was. It breaks like it was made out of porcelain. This stuff is incredibly cold. And when you have something that cold, it seems perfectly reasonable that you would use it to refrigerate your gas. But I think that some of you have noticed that there was something a little bit funny about what was happening with these balloons. And the number of balloons that went in here was bigger than the volume that the box could contain. And in fact, these balloons have turned into pancakes. I can throw them like frisbees. Does anybody remember how many balloons I put in here? 5, I think that's 5. Yellow, blue ones and green ones. Tell me this, how many yellow balloons did I put in? What about, let's see, there's another yellow one. How about orange balloons? There's another one. Anyway, so I could have put balloons in here forever. The point is, let's go back to the PowerPoint now. The point is that if you take anything, any gas, and cool it down enough, then the gas will condense and you won't have any gas molecules or... Ooh! Wonderful, wonderful. Your mother was right. You must never put a closed container of liquid into an oven, and you see just tiny pieces of this are left. This stuff is incredibly cold. But you can't use this kind of refrigeration to slow down the atoms and molecules in a gas, because what will happen will be the atoms and molecules will condense into a liquid or a solid, and you won't have a gas anymore. You won't have this, these perfectly isolated atoms that can give the perfect ticking frequency that you want. But it's worse than that. As cold as this is, the coldest stuff you've ever seen, the velocity of the atoms at the temperature of liquid nitrogen is only half the velocity of the of atoms at room temperature. Now, a factor of 2 is important, but it's not nearly as slow as we want our atoms to be in order to make better atomic clocks. We want our atoms to be moving incredibly slowly. So how are we going to do this? How are we going to make the atoms stay gaseous at the same time that we cool them to temperatures far below the temperature of liquid nitrogen? And of course, the answer is light. What did you expect? The answer is light, and we have seen the answer in the heavens for centuries, because since at least the time of Kepler, people have known that the tails of comets always point away from the sun. And Kepler speculated that the sunlight was pushing on the tail of the comet to push it out away from the sun. But no one knew for sure. Newton denied that that was the reason that that the tails of comets pointed away from the sun, which is sort of odd given his corpuscular theory of light. But he thought it was something else entirely, and people didn't really know until Maxwell came along, and his theory of electromagnetic waves showed that there was, in fact, a pressure associated with light. And we are going to use that pressure in order to slow down the atoms in a gas. And in order to understand how that works, you need to understand 2 different things. One is resonance, the fact that when you shine light on an atom, it will not absorb the light and it will not feel the force from the light unless the frequency is just right. The other is the Doppler shift. If you are moving toward a source of waves, it will appear that the waves are oscillating at a higher frequency. Imagine you were on the beach and waves were coming in to the shore. You could measure the frequency at which they hit the shore. But if you got into a boat and moved into the waves would hit your boat at a higher frequency. That's the Doppler shift for water waves, it works for sound waves, and it works for light waves. And in fact, it is the way in which we know that the universe is expanding, because we know that the light coming to us from distant stars has a lower frequency than the light coming to us from nearby stars, and this shows us that the universe is expanding. We're going to use that idea of the Doppler shift to cool down our atoms. So this is a simplified version of our gas, some of the atoms moving to the right, some to the left. And let's imagine that I am this atom moving toward this laser beam, which is tuned below the resonant frequency of the atoms. Now that means that if I were at rest, I wouldn't absorb the light very much, but I'm moving, and I see the frequency of this light shifted up by the Doppler shift, so it's closer to my resonant frequency, and I absorb it. This atom, on the other hand, that's moving this way, if it absorbs the light, it would speed up, but it doesn't absorb the light very much because the frequency is wrong. The Doppler shift has moved it further away from resonance. Now, in order to make this process work better, we just bring in a laser beam from the other side. Now, both of the atoms preferentially absorb light from the laser beam that opposes their motion, and we can bring in more laser beams from top and bottom and back and front, and now no matter which way the atom goes, it absorbs light preferentially from the laser beam that opposes its motion. Steve Chu, who spoke yesterday, first accomplished this in his laboratory in Bell Labs in 1985, and he called it optical molasses because the atoms feel as if they are in a viscous fluid. And I just want to point out that the Doppler effect is something that arises naturally from the wave nature of light, something that we celebrate from Fresnel. It's not 150 years ago, it's 200 years ago, right? Now, another thing that we learned from Einstein is that the light is absorbed in quanta that we now call photons. And that quantized nature of the light leads to a heating because there's a randomness that comes in the process that comes to us from Einstein's particle theory. And he worked all of this out in 1905. And the balance between the heating and the cooling leads to a temperature, which for sodium atoms, which were the first atoms we cooled in this way, could be as low as 240 microdegrees above absolute zero. Now think about that, 240 microdegrees above absolute zero. This stuff is the coldest stuff you've ever seen. It's 77 degrees above absolute zero. And we're talking about getting down to temperatures that are 300,000 times smaller than liquid nitrogen, which is the coldest stuff you've ever seen. So, this is incredible. How does it work? Well, here's a picture from our laboratory of a gas being laser cooled. So this has laser beams coming in from all directions, and the atoms are stuck in the optical molasses here. And the question is, what is their temperature? How do we measure the temperature of something that is that cold, that is as cold as 240 microdegrees above absolute zero? Well, Steve Chu developed this technique. You put the atoms into the optical molasses, they're moving around, but they're not getting very far because the molasses is so sticky. But when you turn off the laser beams, then the atoms expand freely, as any gas would expand in a vacuum. And the faster the atoms are going, the faster they move away from the intersection of where the laser beams were. And when you turn the laser beams back on, the hotter the gas is, the fewer atoms will be left. And you can calibrate this and measure the temperature. And Steve Chu did that, and he measured a temperature of 240 microdegrees, exactly the temperature that the theory predicted was the coldest possible temperature you could have. Well, we repeated those measurements, and other people repeated similar measurements and found everything to be consistent until we started to do some more careful experiments. And when we did the more careful experiments and measured the temperature more carefully, quite to our surprise, in 1988, we discovered that the temperature could be much colder than had been predicted. Now remember, the whole idea was to make the atoms as cold as we could using light. And we had apparently made them colder than we could using light. This was clearly a violation of Murphy's Law. And we didn't know what to do. There were lots of discussions about what was the cause of this extra cold cooling. Well, the heroes of this are shown in this picture. Claude Cohen-Tanucci and his young colleague Jean Dalibard, Steve Chu and his colleagues figured out what was going on, and guided by their theory. And I also wanted to mention on this slide, I haven't been mentioning very many other people that have been involved, but many, many people have contributed to laser cooling and trapping, and it was just this group of people that was recognized with the Nobel Prize. But guided by their new theory, by 1995, we had cooled cesium atoms down to a temperature of 700 nanokelvin, which was 200 times colder than was expected for cesium. Each atom has its own lowest temperature. And we'd cooled it down to 200 times lower than what was thought to be possible. So think about this, 700 billionths of a degree above absolute zero. My friends, that is 100 million times colder than liquid nitrogen. And liquid nitrogen is so cold that it boils when you pour it out on the ground. It's the coldest stuff you've ever seen. And I hope you're having a wonderful experience over here with all this, this cold nitrogen. This stuff is incredibly cold, and we got it 100 million times colder than that. This is 4 million times colder than the temperature of outer space as determined by the cosmic microwave background. And remember, the discovery of the cosmic microwave background is one of the things that we're celebrating as an anniversary of 50 years. How fast are these atoms going? At this temperature, these cesium atoms are moving at a velocity of less than 1 centimeter per second. So let me remind you, here's the old atomic clock. The atoms are moving along a little less than 200 meters per second. It's milliseconds to go from here to there. Now we have atoms that are not moving at 200 meters per second. They're moving at 1 centimeter per second. What kind of a clock can we make if we have atoms that slow? And the answer is no clock at all, because the atoms fall like rocks. If you have something moving at 1 centimeter per second and you let go of it, it will just drop straight down. But fortunately, many, many years ago, Gerald Zacharias at MIT had the idea that if you, instead of shooting the atoms sideways, if you throw the atoms up the same distance, you see, you throw something up a meter and it comes down after a second. And so this is called an atomic fountain, because it's like these jets of water that go up and then come right back down. And here is a picture of an atomic fountain in our laboratories in Boulder. Don Meekoff and Steve Jeffords made this atomic fountain, and they cool the atoms here, they toss them up here, they come back down after a second. And clocks like this are the best primary atomic frequency standards ever made. Here is another version of that operating here in Paris at the Observatoire de Paris. And there are clocks like this all over the world. For example, in Brazil, I see my colleague Vanderlei Bagnado has a fountain clock similar to this. And these clocks, the best of them operate with a fractional uncertainty of a part in 10 to the 16. That means they're accurate to 1 second in 300 million years. But that's not the end of the story. Dave Wineland trapping a single ion and operating now at optical frequency, not at microwave frequency. So here is where light comes in again. Operating at optical frequency was able to operate for the first time a clock going down into the 10 to the minus 18 range. Laser-cooled atoms, or ions I should say, operating at about 8 times 10 to the minus 18. But that's not the end of the story. Junyi and in other laboratories all over the world is trapping neutral atoms using light. So by intersecting beams of light, he makes a kind of an optical lattice for the light. So the light traps the atoms, and the atoms are ticking at optical frequencies. And these clocks are now operating at 2 × 10⁻18 fractional uncertainty. 2 × 10⁻18, that is 1 second in the age of the universe. And it's all because of light. Let's bring in Einstein again. Remember, Einstein's general relativity, one of the things it taught us was that there is a gravitational redshift. Clocks that are operating lower at sea level will run slower than clocks that are operating at the top of a mountain. When I joined NIST in 1978 as a young man, the best clock could barely see the difference between sea level and Boulder, Colorado, where the best clocks were made. Today, the best clocks can see 1 inch, 2.5 centimeters. This has all been made possible by the application of light to cool the atoms and by changing to using light to being the way to probe the atoms and to have the atoms ticking at the frequency of light. By the way, if we didn't have Einstein's theory of general relativity, the global positioning system wouldn't work. The corrections that are made to the satellite's time due to general relativity are absolutely essential. You would be off by kilometers if you didn't have the theory of general relativity. And it's light that's made the difference. The 2005 Nobel Prize was given for the technology that made it possible to measure the frequency of light. So light has been at the heart of this entire story. And I just want to emphasize that the story of cooling of atoms and the story of the improvement of time has been a story of light from the start. And it's a story that spans the entire world, and it's been written by hundreds of brilliant researchers in literally hundreds of laboratories all over the world. Time in 2015 is truly an international story of light. But now you may ask yourself, where do you store the coldest stuff in the universe? Imagine that I want to put these cold atoms into some sort of a container. Imagine that this bowl is the container in which I want to put my atoms. Now, if the container were cold, what would happen would be that the atoms would simply stick to the inside of the container, and that would be useless to me. I couldn't make a clock out of that or do any experiments with them. On the other hand, if the container were hot, that means that the atoms and molecules in the container itself are moving around very fast. And when the atoms hit it, they would get the energy of those atoms and molecules and heat up, and I wouldn't have a cold gas anymore. So how do I hold those atoms? Let's zoom in on this apparatus right here. And the answer is, I hold them in a bottle, in this case a magnetic bottle that has no walls, that holds them without touching. So what we have here is a big magnet, and what we have here is a little magnet. This little magnet represents our atoms, because it turns out that many of the atoms that we use are magnetic. So it represents a little atom. Now, the big magnet is pushing up on the little magnet, and right about here, the magnetic force balances gravity, and it should simply levitate. So if I let go of it, it should float. And when I let go of it, it doesn't float. Oh, I have a disaster here, because all the pieces fell off. So let's hope that things are not too bad. So the point is that anytime you try to do this with ordinary magnets, the magnet flips over and it gets attracted instead of being repelled by the magnet, and you can't levitate things. But our atoms are not just little magnets, they're little spinning magnets, and as you know from your childhood, a spinning top doesn't fall over. And so if I spin the magnet, it will stay in the same orientation, and I can levitate my atoms. But no, you shouldn't applaud, because any two-bit magician can levitate a woman and then pass a ring around her, carefully avoiding the wires that are holding her up. But you've never seen a magician do that. You see, this is the real thing. That is how, thank you. Let's go back to the PowerPoint now. That's how we hold our atoms. I'm going to go quickly now to the end using these traps, which are now also done with light, not just with magnets. So light comes in again. We evaporate the atoms by letting the most energetic atoms escape, and we come to another of Einstein's predictions, a phase transition where a large fraction of the atoms stop moving. So now let's look back at this odyssey on which we have been of cooling atoms down. Here is a logarithmic thermometer. Every tick mark on this thermometer represents a factor of 10. At the top, I have the surface of the sun, about 6,000 degrees. Not the hottest temperature in the universe, but a very hot temperature. And you see room temperature is just a tiny bit colder than the surface of the sun. And on this scale, liquid nitrogen, the coldest stuff you've ever seen, boils when it pours out on the ground. Even Serge is afraid of this stuff. And it's only a little bit colder than the surface of the sun. Even outer space is only a little bit colder than the surface of the sun. The first experiments that Steve Chu did with optical molasses produced temperatures colder, more cold compared to outer space than outer space is compared to the surface of the sun. And that was just a start. Now, approximately 10 years ago, the temperature got down to 500 picokelvin, 1/2 of 1/10000000th of a degree above absolute zero. And today, even colder, a few hundred picokelvins. And maybe in the next decade, experiments in space will get down another factor of 100 or more colder. What are we doing with these things? Already making better clocks, guiding the global positioning system, cold chemistry, testing our fundamental understanding of nature, quantum information, quantum computers, quantum simulation. But perhaps most exciting is that possibly the International Year of Light will inspire young people to think of even more exciting ideas. And so we come to the end. Here is a picture of my research group, people from all over the world working on new aspects of how light can make things colder and open up whole new vistas of research. And this is true in research labs all over the world, including here in Paris. And so we come to the end, but it's not the end. It's really just the beginning. Thank you very much. Thank you. So,